So, okay.
Yes.
Dear Jüri, it's a real pleasure that you accepted the invitation to give a talk online. That's a pity, but I hope soon there will be some possibility to make it better. And we are very interested into your work and evolution models. So thank you for giving this talk. So maybe I give you the word.
Yeah. Thank you, Paul. Thank you for inviting me. I hope everybody hears me. And I hope everybody sees the slides here, yes. And so it is the joint work with Chris Watkins, who is also present here, Chris Watkins, and Fabio Suca and Daniela Bertacchi. Chris is from Royal Holloway University in London, and Fabio and Daniela are from different universities from Milano. And I myself am from the University of Tartu, Estonia. And I'm going to speak a little bit about a particular evolution model that Chris and myself, we have been working out. And I must confess in the very beginning that I do not consider myself as an expert of evolution models, but so I'm quite a new kid in this block, but I'm really fascinated by this theory, and hopefully can something to contribute. So let's get started with mathematics. Our model starts, we have a finite set of let's call them types or genomes. I try to be as less biological as possible, just let's call them types or genomes. So we have finite set, it's very important that the set is finite. And the first ingredient of our model is a stochastic process, which we denote by psi. It's an exchangeable stochastic process. It's X valued. So it takes values in this finite set. And this is our breeding process. So we call it breeding process that models the breeding. And so let's introduce some notation for any population of n genomes. Then we have n individuals from everybody has a genome, a type from this set. So this is the probability that the first 10 elements of this process take exactly those values. So the process is exchangeable. So any permutation of these values will give exactly the same probability. And this whole theory is based on the celebrated De Finetti theorem, which is that every exchangeable process can be represented as a mixture of IID processes. So the De Finetti theorem says that there is a prior measure, probability measure on the set of all probability distribution which on this finite set. So in our case, the set of all probability distributions is just simplex. And the De Finetti theorem says there is a prior measure on simplex, so that this probability distribution for any n, for any types, is a mixture of IIDs. So, and since the order is not important, we can denote this distribution as the following: just nk is the number of k types in this vector, and the number of k types sum up to the n. So there's nothing new. It's a famous De Finetti theorem. So basically any breeding process, any exchangeable process is uniquely characterized by this prior measure. If this prior measure happens to be concentrated on particular element of simplex, then the process is IID with this measure. But in general, it is mixture of IID process. So the pi measure comes from that. And it's a very general process. And in our setup, there is a very important special case of this process, namely when the prior measure is a Dirichlet measure. And in this case, this this process, the breeding process, is nothing that, it is called sometimes Dirichlet categorical process. If K is 2, it's a beta-Bernoulli process, but it is also can be considered as a generalized polyurn model. And it's very well known that the probability that given the conditional probability of seeing a type K, given the history up to n, it's equals to number of those K types in this sample plus the prior alpha K divided by the whole n plus the sum of those parameters of Dirichlet process, which are non-negative. And the Boyer-Urn says that if those are all integers, so we think that we have a Urn with K with which contains alpha 1 poles in color 1 and alpha 2 poles of color 2 and alpha K poles of color K, and then we pick up one pole, record its color, that's color is X1, and put this pole back together another pole with the same color, and then we take next ball from this urn and record this color, it's X2, put it back again with another ball with the same color, and that's the famous Boyer-Urn model. And but obviously those alphas need not necessarily be integers, so that's why it's a generalized Boyer-Urn model. It's a well-known, very well-known model. And since it's exchangeable, because the order it follows that it's easy to see, I don't go to depth, that the probability that we observe in particular sequence of types or colors, it can be represented in this way. It maybe this formula looks awful, but it's very easy to show. And since this is exchangeable, so the order of those elements does not matter. So it's basically equivalently, we can this probability represent as the probability of the cones. So just any X vector that have n1 elements of color 1 or type 1 and 2 elements of error 2. So any such a vector has the same probability, and so that's why we have this factor, and that we can call it just a vector of cones. So this is a very special case of this, our breeding model when the prior measure is a Dirichlet measure. And why it's a measure? Because that connects our model with very famous evolution model, which is called the Moran model. So in my opinion, the Moran model is rather a class of model than one particular model, but it all starts with very basic Moran model. So let me recall or introduce, if you don't know, that the very basic Moran model is the one of the two fundamental evolution model next to Wright-Fisher model, but those models are very similar. Exactly that the Moran model is in individual level. So we have a population, again, we have K types or K colors or K genomes. We have a population consisting of n individuals, and this population has n1 genome, n1 number of individuals having the first genome, etc. And this is considered as an urn consisting of n poles of K colors or types. And 2 poles are drawn with replacement. So we take one pole out of this urn, we record its color, we put it back, and then we take another pole out of this urn, we record this color and put it back as well. And so the first pole we take, and we call that this type, this color dies. So we take a pole of this color out, and we replaced no, this is breeds, sorry, that one of them is going to taken away, and another pole with the other color is going to be added to this model. So the probability that that one E color pole is added and one J color pole is taken away is exactly this. So that's the probability that that the NE color is taken in the first place. So that's the breed, and the J color pole is taken also, and that's we call that dies. So that's a very basic model. So this is the probability that the NE number of E colors have one more. So that's the transition. We consider this as a Markov chain, which is this is a state space, and this transition has this probability. It's very simple, but just two balls taken out with replacement. And when we consider this as a Markov chain with this state space of all types, a number of types, then you can easily see that this Markov chain is not irreducible. It has a k absorbing states, namely if all poles are the same color, because if the all poles are the same color, whatever you take only one types, and one type is dying at the same time is born and nothing happens. So sooner or later, this basic Moran model will end up with one of those absorbing states, and this is called in this literature fixation. So it's not very interesting model. It's sooner or later it is one of those states where all balls are the same color, or genotype are the same thing, and this is called fixation. And the standard matter in the textbook is what's the probability of the fixation, what's the average time for fixation, etc., etc. So that's the basic Moran model. It's very basic type-wise. So one ball is taken out, that's going to die, and the other ball is taken out, that's going to breed. So in order to get it more interesting, the people add mutations to the basic Moran model. And again, as I said, there is a various ways of adding mutation to the very basic Moran model. And one of those ways, among other ways, is the following, that let Uy be a probability, small probability, that we take any type of any color of ball out of the urn, and this randomly mutates into the color or type I. So this sum is the overall probability of mutation. And then this transition that the I ball is born or breed, and J ball is going to die, is the following. So this is exactly the probability of death. So we pick up the ball and we record this number, and if it's J, it's going to die. But the breeding probability is now different. So this is the probability that nothing happens, no mutation. So if we want to breed I color, we have to take it out of the urn, that's the probability. Or we take something else and it breeds and it mutates into the color E. So this blue term here is now the breeding probability, that the E color is to breed, and J is the J color is going to die. So now this Markov chain now is irreducible, because even if we have in the urn all poles of the same color, there is a chance that it mutates randomly into other color, and so we have a irreducible Markov chain. And this Markov chain is very easy to show has a stationary measure, which is which is exactly the same stationary measure which we saw in generalized Boyer-Urn model. So it has the stationary, the Markov chain has the stationary model, but what is alpha? Alpha's here. So alpha k is just defined using the UKs in the following way. So there is a one-to-one correspondence between alpha k and UK in this way. So this is now the stationary probability, stationary measure of this Markov chain, which is now irreducible and has stationary measure. So this is this fact establishes the connection with the Dirichlet categorical process, our breeding process, and the Moran model with this particular kind of mutation. So the probability that type I is now born, recall, it is the same probability. It is either something which we take out of the urn mutates into the type I, or we take type I out of the urn and it doesn't mutate. And when we do this replacement here, we replace this, we get exactly the same probability that the Boyer. Yeah. So when we add this kind of mutation to the Moran, basic Moran model, we are bingo, we are in the Boyer or Dirichlet categorical process. So including mutation in a certain way into basic Moran model, it's Dirichlet categorical breeding process. And what does it mean in terms of Boyer? You can interpret those. So the initial balls, which are in the step 0 in this Boyer, they are called prior ball. And even we take only the one color out. So suppose we always take the type 1 out, so we have a population of consisting all of type out. There is still chance that we take one of the prior pole, which is different type, and so it's no fixation in this case. So there is a one-to-one connection between moral model and the Dirichlet categorical process. And I would like to point out there are other ways of including mutation into the basic moral model such that the stationary distribution would be the same. This one, this guy here. So the transition matrices maybe are different, but the stationary distribution is the same. So, but also I would like to stress out that our breeding process is more general than, because it allows not only the Dirichlet categorical process, but prior, but very general mutation breeding, all other priors rather than Dirichlet. So that's our mutation. That's why we call this a breeding process, and which naturally involves mutation. We do not have to include mutation separately, as it typically it's done in evolution models. Now, any evolution model consists of two parts: mutations and selection. So the mutations are due to the Gregor Mendel, the monk in Brno, and selection is due to Charles Darwin. So we already discussed a little bit the mutation and the breeding part, and now let's go to the selection. So what we have the population consisting of n types. The next type of the element is bred from this breeding process, this Xi process. It might be Dirichlet or not, something else. Now the population consists of n+1 individuals, but we want to have population size constant, so one of those guys has to be discarded or die. Now the probability of being discarded depends on the fitness of type. So to every type, to every color, or to every genotype is associated a number, non-negative number, which we call fitness. So we order our type so that the type number 1 is the most fit type, and it's strict. There is a strict inequality. So we want when the only one type is the most fit. And now there are several ways which we call selection scheme to incorporate the fitness into our selection, our model. So those are two selection schemes which are in our article, which Chris has successfully coded or programmed. The first is single tournament selection. It's we sample a new kid, new type, and this type has picking up randomly uniformly. I'm sorry, this uniformly has to be not here but here. Picking randomly uniform distribution one of the existing members of the population, and is going to have tournament with this guy. And when it wins the tournament, then this guy, the loser, is replaced by xn+1. But if he loses the tournament, then nothing happens. And the probability that this guy wins the tournament depends exactly on the fitness of this guy. So the probability that this new member wins the tournament is the fitness of this new member plus the fitness of the member he chooses to fight with, and is divided by the sum of those fitnesses. So the more fit is the new member, the more probably is that he wins the tournament that is replaced existing one. And the second selection scheme is that we just, again, we sample new member, and then we sample out of all n+1 elements. Now we have n+1 elements, individuals in the society, in the population. We sample one of those, but not with the equal probability, but the probability which is proportional to inverse fitness. And if it happens to one of if we pick up one of which is not the newborn member, then we just replace the guy with the newborn member. So again, the more fit is the newborn member, the more probably is that he replies some element in the existing population. And both schemes introduce a Markov chains. Now the state base is those vectors, And it's easy to show that the Bose scheme, I don't show any proofs here in my talk, satisfy detailed balance equations. And with stationary distribution is exactly this guy. And what is the stationary distribution? So this is the breeding term. This is the probability that this population, this particular population has been bred, times the fitness term. So that's the multiplication of the witnesses of single individuals, and that's the normalizing constant. So this is the stationary distribution under those schemes. Both scheme. So the both scheme take different scheme define different transition matrices, but the same stationary distribution. And again, this is exchangeable. So there is nothing depends here in the order. We can equivalently consider this measure on the set of counts. So this is just the number of counts. And so we have a count version of the same measure, but we just have to divide by all the number of counts. And this is a one particular element. And this is now typo instead of xi here must be n, obviously. So because this is one particular population where we have n1 counts of ones, etc. And all permutations have the same probability, and that's the number of permutations. And that's a typo. There should be n, not xi. So there is a population version or the count version, but the one-to-one correspondence. And what's the connection with the Moran models? Because really we would like to be in the classical framework of the evolution model. Again, when this xi is Dirichlet categorical process, then recall that the probability that I type is born, I color is taken out, or the I type is born is this probability. It's nothing. It's the ball with type I is drawn from the UR and no mutation, or something else is drawn, or this is the same thing is drawn and this mutates into the color I. And under the single tournament selection, the probability that now the type J is chosen to die. So this new pawn replaced J is this guy. So that's the probability that the type J is chosen to fight, have a tournament, and that's the probability that this type J loses the tournament to type I. And under the inverse fitness selection, the other selection scheme, the probability that we choose exactly the type J to die is the following. And so when we now include all those selection schemes with our mutation, then we have the following transition matrices. Now this is now, sorry, this is now the transition matrix in terms of type again. So it means that that's the probability that type 1 is born and type J is discarded. So this transition has the probability, this probability. And under single tournament and under this other scheme, this has this probability. Those are different, slightly different transition matrices, but they have the same stationary distribution, which is the famous, the count version of our familiar guy. So again, when we have our Moran model and we do the selection in a certain way, we will end up with the same stationary distribution. And I would also say there is many more possibilities apart from those two selection schemes to put the W, the weights into this transition so that the stationary distribution is the same. So the transition matrices might be different, but the stationary distribution is the same. So if you run this thing long time, you end up with the same distribution. So this stationary distribution is our main instrument of object of interest. It's our thing we are going to work with. And there is also a continuous time version of the same thing, because often the Moran model has a continuous time. And I very briefly just say the continuous time model. So we have a model again with n individuals, and every individual has a lifetime which has exponential lifetime with distribution depending on the type of the individuals. So expected lifetime is exactly the weight of this fitness of this individual, and less fit individuals have shorter lifetimes. And when an individual, say XL, dies, then it replaced to something else, which is generated. Now there was one less individuals. Now we first it dies and then it generated one less. This L1 is taken out. It's generated from new, and it's replaced. Maybe it's the same type, maybe it's different type, but so it goes. And so it goes on like that. Then it's again the next guy dies, and then it's replaced. And so it goes on, and then we have a continuous time Markov chain. And again, you can say that the chain has the same stationary distribution. So it's the same stationary distribution appears, and if we have the state base, not the population but the counts, and if there is a two types, then typically in the literature we have counts are n1, the number of first type, and the number of second type, but the number of second types is totally determined by the number of first type. So there is a basically Markov chain which has state base, the number of first type 0, 1 to n, and there is a transition rates. You can see, there is, I skip the technicalities, but it sees that this Markov chain has it's a birth-death Markov chain, birth-death chain, which has a transition rate, something like that. That's the breeding process. And birth rate, something like that. And if you have a Dirichlet categorical, since K is 2, a beta Bernoulli process, then we have this kind of birth date model, and that's very close to the classical Moran model, again, which you can find out the literature on continuous time. So to recapitulate my first part of my talk, we introduce a general evolution model that naturally incorporates this mutation. So we do not have to add any specific mutation. It's inside the breeding process. It generalizes Moran model because Moran model is a special case of it, satisfies the detailed balance equation, and has the following stationary distribution, which is very easy to interpret. It's a breeding terms and fitness term and normalizing constant. So that's the main message of this talk, that we have this model. And now we are going to do something with this model. Now our problem, the question is, this measure, the limit measure, or not the limit, but the stationary measure is the main study of our interest object. And of course, since this is the stationary, this is the breeding process has this definity theorem, we can write it 10 different ways, and we have written it in different ways, but this is one way, just to write it down. There is this now prior. Actually, the W and pi are two ingredients. And since we have an equivalent version of the count version, we can just divide everything by n, and now we have a measure on the simplex, so, which we denote Q, and Pn is on the population, and Qn is on the simplex. And the difference is the domain of the Pn is depends on the n, it's the population of size n, all population of size n, but Qn is always defined on the same set domain, which is simplex. And the questions actually, I was asked by Chris a long time ago, what's happens with this stationary measure with Pn or Qn when the population size increases. And for limit theorems, we let the W, the weight, depend on the n, and we rewrite in the following way. So you can always write it the following way. Of course, there is an assumption that this logarithm of this is negative, but non-negative, and we put here divided by n lambda. So if lambda is 0, then this guy disappears, and that's constant weight. But if lambda is not 0, then the weights depends on the n, and the bigger lambda, the quicker the differences disappear between the weights. So if it is very big, lambda is very big, they're very, very equal. So basically no differences. And so in what follows, all those measures are defined with respect to those weights. But when we go to the limit theorems, we have to define what do we mean by limit, the modes of convergence. So with Qn, it's easy. Qn is defined on the same domain of the simplex for every n, and the question is there a probability measure that it weakly converges to this limit? Very well-defined question. For Pn, we consider the existence of limit process. What do I mean by that? So remember, we have a Pn is a population consisting of n elements. P is a population consisting of one element. So basically, the first they are obviously of the same distribution of elements due to exchangeability, but x21 and x11, so they're different. So for every n, we have a population consisting of n elements, and now we ask, is there a stochastic process, a limit population, so that the marginals, so that for n, so if we let n go to infinity, we take the first m element, and do they converge weakly to the first m element of this limit process? So basically, is there any process such that that the first elements of the population converge weakly to x1 and the second elements and the first pair, etc., etc. And since everything is finite, it's equivalent to the existence of probability measure on the set of all sequences, so that those marginals for every m converge. And if this holds, we say that the limit process exists. So that's now we have specified our question, but we do the limit theorem. And now we have our first limit theorem. And let me just state the theorem first, and then let me try to explain what the theorem is. So this is called constant priors, because the priors are now pi measure, it doesn't depend on the n. And we assume that the support of the prior is the whole simplex. That's necessary assumption, a natural assumption. And so we have, there is a three phases. If lambda is zero is smaller than 1, if lambda is equal to 1, or if lambda is greater than 1. If lambda is smaller than 1, then the limit process exists, but the limit process has only one trajectory consisting of ones. So it's not stochastic process, it's just a deterministic process consisting simply of ones. If lambda is equal to 1, then the Q measure converges to a certain measure on simplex, and the limit process is the mixture of IIDs with respect to this simplex, this measure, P bar. And what is pi bar? What is pi bar is, this is the integral with respect, and this is pi bar is defined in the following way. So it's really a measure, it's not non-generated measure. So, and if lambda is greater than 1, then Qn converges to the prior measure, and the limit process exactly equal to the breeding process. So we see here the phase transition. This is our phase transition theorem, which says if lambda is very small, smaller than 1, which means that the lambda is either the W's weights are constant or the difference is very slowly, then the limit process has only one trajectory, only the fittest genotype survives. So the whole population would consist of the fittest type, because the mutation do not have any, breeding doesn't have any influence at all. Only the fittest genotype survives. If lambda is again greater than 1, that's the other extreme, then the differences between fitnesses decrease so fast that the influence of selection disappears, and the limit process equals to the breeding process. There is a selection does not play any role. And the interesting case is if lambda is equal to 1, and then they are all interesting, then the limit process and non-degenerate prior. Then it's really not the ID process. So in a sense, this lambda equals to 1 is a proper scaling, and in the literature often it's taken, WK is taken 1s plus SK when SK times K is going to some constant, and then we see we are almost as we had. Now you can find something like that in the literature. So that's our first phase transition. Remember the phase transition in terms of lambdas. lambda is, yeah. Now we go to the second theorem. Now, because here this theorem, I repeat, this theorem holds for any prior. We didn't assume any specific type of prior. It's any measure. The second theorem goes about the Dirichlet prior, because as we saw, the Dirichlet prior is a very important special case, because it connects our model with a Moran model, and that's what the literature covers. So it's the special case. So we take the weights as previously, like that, depending on the lambda. But now we consider the Dirichlet priors, and here is also the lambda. The same very lambda is here. So there is a weights so they are increasing. If lambda is not 1, then it's increasing those. So let me recall what does it mean actually if those parameters of Dirichlet increase with n. So alpha bar is still the sum of these alphas, and so in this case the Dirichlet prior has density. With respect to Lebesgue measure in simplex like that, it's proportional to n. This goes like that. And just to recall that if we have a random vector with this distribution, then expectation of this random vector is the averaged alpha. So this is probability measure. And the variance of one single element, the marginal y chi, is basically the same thing divided by n tower. So if lambda is smaller than 1, so and then if n increases, this variance decreases. So the bigger is n, the bigger is so-called the concentration parameter. The more the Dirichlet prior is concentrated around this expectation. And also given n, the lambda varies. With the lambda, we can tune how much is it concentrated around the expectation. So it tunes the distribution. And if lambda is 1, that's the constant prior case. So we put the same lambda on the weights and on the prior. One. So again, there is a lambda, and there's n 1 minus lambda. The same lambda. And now the second theorem, Dirichlet prior, the second theorem, again, phase transition theorem. If lambda is 0, then Qn, which is on simplex, converges weakly to a delta. So to a delta measure, which is concentrated one particular probability measure. And this particular probability measure is defined there. It's a proportional to Wk. So it's the weights times Q star K. So basically Q star K's are the following. So this distribution combines alphas and W's in a certain way. You can, in RK, you can multiply this with Wk. This is the parameter that makes this probability measure. And so it's a probability measure, and then the limit process is an IID process with this particular probability measure R. Now it's a complicated, not complicated or not, but that's the probability measure has this way. It involves the weights and alphas, and that holds only if alpha is 0. If alpha is greater than 0 and smaller than 1, then the limit process is IID process with another probability measure at Qn obviously converges to the delta at another probability measure, where the other probability measure also involves obviously alphas and the weights or logarithm of the weights a little bit differently way. So they are different measures. And one corresponds to alpha equals to 0, and the second corresponds to alpha equals to greater than 0, smaller than n. And if alpha is equal to 1, then it's already case we are considered, because in this case the prior is constant, and we know that the limit process is not anymore IID process, but it's a mixture of IID process And in this case, the density mixture has a density is proportional to Dirichlet density times, and factor depends on the weight vector as well. So again, this is our second phase transition theorem. It says that when lambda is 0, then the limit process is IID process with certain probability distribution. If lambda is between 0 and 1, the limit process is IID process with another distribution. And it is interesting, to me, counterintuitive, that the limit process does not depend on the lambda. I was always expecting that the limit process on the limit, this thing depends on the lambda, but it doesn't. However, the speed of the convergence does depend on the lambda. And the last case, when lambda is 1, it corresponds to the case of the previous theorem, and the limit density is something like it is like that. So again, the 3 phases depending on the lambda. The last one, this density can be found in textbooks for both Moran and Wright-Fisher model. Now, why it can be, if I claim everything is new, why it can be 5? Because this is the case, as I said, that sometimes in the literature it is taken this sort of weights like that, satisfying this constant, and it's exactly the case lambda is equal to 1. And if we have a Dirichlet, if we have a Moran models, then we have a Dirichlet prior. So this particular case is covered sometimes in the literature, and in many textbooks actually. It's sometimes called the Wright formula, but it's interesting that typically, and now I'm not saying that always, but as far as I have seen, the references for the proofs, they are referred to the diffusion approximation, which is very difficult way to prove it. They approximate the process with diffusion model and a lot of technique. And our proof, it's very simple. It's a really very simple proof. The mathematics here is not very complicated. It's a really simple proof without any approximation, without diffusion approximation. So I'm not claiming that you cannot find this in the literature. I really don't know the whole literature. But typically in the textbook, it is referred that this can be done by diffusion approximation, because I believe that in 30s of the last century, the guy called Wright, who was a pioneer in evolution, used diffusion approximation to prove this kind of stuff. But actually, you don't need it. It's very simple. You can do it simple. So this is now the second theorem. So we have 2 phase transition theorems. And one might wonder what happens if you consider different lambdas. So we had several lambdas, the same lambdas from the weights and from the prior. And what if we take them different? But there's nothing interesting happens actually. Again, the same extreme cases. If lambda 1 is strictly bigger than lambda 2 and lambda 2 is smaller than 1, then the limit process is an IID process with the distribution, which is the expectation of this expected value of this distribution. Again, this is the case where the influence of fitness phases, there is no fitness anymore. So it means that the fitness decreases so fast that differences that it vanishes. On the other case, if lambda 2 is bigger than lambda 1 again, then there's no influence of breeding. So only the trajectory has 1, 1, 1, so only the fittest genotype. So the whole population would be the same type. So basically, the only interesting case is something more meaningful come up is again the case when the lambda is equal to lambda. And that's why we consider this case above. And so far, so good. And this is the context, very large, the main context of our article with Chris Watkins. And the last minutes of my talk, I would like to devote to the question, what happens if we have uncountable number of types? So I'm consider myself as a mathematician in the nature, and okay, it's very easy, as I say, the proofs are not very technical. I do not need any diffusion approximation, prove those things, and though generally we would like to generalize if the number of types is not finite, but at least countable and uncountable. So as a mathematician, we would like to take very general space like a Polish space or or D are just a compact set. So, and it turns out that's way more difficult problem. It's really, that's why I included the Fabio and Daniela from Milan and also probabilists to help me out, because it's really technical. So, but it starts, basically it's the same. So we have a X value, which is now uncountable. A changeable breeding process with certainly prior, so the definite theorem holds true. But now the P is not the simplex, but the space of all probability measurement. That makes it difficult. It's a huge space. We must have a Prokhorov matrix there to make it metriceable, etc., etc. And now the special importance case is when the pi is Dirichlet process. Dirichlet process is a random. It's a measure on pi of the set of all probability measures, and it typically has two elements. It's a non-atomic probability measure, which is a base measure, which is alpha bar, and the m is a concentration parameter. And let me just recall that if we have a random measure with this probability, it means that for any finite partition, this random vector has a Dirichlet distribution with those parameters. And why this Dirichlet process, in my opinion, is really meaningful in this evolution model settings. If we have the breeding process with Dirichlet process as a prior measure, then what's the probability that we cannot speak anymore that the newborn is equal to A because it's uncountable. So it belongs to a set. This C can be represented as the following way. It's a well-known fact, you can find it everywhere. So it's the base measure, the base measure probability of the set A, and the base measure multiplied by this number. And so this is the Dirac measures on the atoms, on the existing elements, and weighted like that. So it's maybe too complicated formula to understand, but the point is the following. If we have out of the n values which you have seen on the population, there are repetitions. So let's suppose we have a k distinct values, k different. So there is repetition. With those be the repetitions, frequencies. So the conditional distribution of having a new member, a new genotype in this case, is with probability m, which is the concentration parameter, divided by n plus n. N is the number of elements in the population. It's a draw in the base measure. But recall, the base measure was non-atomic. So it's really a new guy. It's really something you haven't seen before. It's really a mutation. As much as I understand, the mutation is a type we haven't seen in our population so far. It's really new type. And with this probability, the more we have seen those guys in our population, the more probable is that we see this guy again. So since we have a base measure doesn't have atom, so the mutation now, this process really incorporates this mutation as we understand it, as I understand it really. So mutation is something, a new genotype which hasn't seen in the population. And once we have seen it population, it repeats itself. It's coming to with certain probability again, exactly as Gregor Mendel observed. So it's the mutation. It's really naturally incorporates the concept of the mutation. And what's the probability to see new element? So if we now take m c constant times n, as we see that, and then in this case, the probability of mutation is constant. So with this little constant c, it's independent of the n. For any large n in the population, there is a certain probability that we see the mutation, something which we haven't seen and something which really new, but once we have seen in population, it starts to repeat itself. We see it again. So that's what, I am not biologist, that I understand the mutation. So that's why I believe it's very nice model. And now the mathematics. Now, since this is uncountable, so we cannot speak any about Markov chain and transition matrix, but we have still Markov chain, and with uncountable state space, we have transition kernels instead of transition matrices. And those transition kernels for both selection schemes can be defined very easily. And you can prove, it's not very difficult, all those kernels, again, they satisfy detailed balance equation, which with kernels looks like that. Those are just measurable sets. And the stationary distribution is pretty much the same, but I put the red n, stressing out that it depends on the n. But it's really, you can write it like that. So it's a counterpart. You can generalize. It's not that big a problem. The fitness is now again in the same way, but now this phi is continuous bounded unique function, which has unique phi minimum. We use it's the unique minimum. So this is the most fit, unique most fit type. And the theorems, actually the first phase transition theorems holds true basically the same way. So there are three phases. If lambda is small, then under some additional mild assumption, the limit process exists and has only the trajectory which consists of most fit individuals. And if it's compact, we need some, well, work is still in process and we need some additional technical assumption on compactness, then we can prove the Q measure as well. But the idea is the same. Most fit individuals survive, and the population is very boring. Only Chuck Norris's, or I don't know, the guys who are the biggest fitness lives. If lambda is too big, then the limit process is the breeding process. Now fitness has no role anymore. And in the case lambda is 1, then we have the same limit process, and under the complex we can prove everything else. So this is directly generalizes the previous one with finite case, but the proof I stress out is way more, surprisingly more involved, surprisingly more technical, and you know, you have to work out all this measurability and continuity and all this kind of issues. And I finish with the counterpart of the second theorem, which really becomes now interesting. We have a Dirichlet process prior. So and if lambda is 0, so the Dirichlet process prior is exactly as I described. It has a constant mutation probability. There is in regarding how big is the population, there is a certain fixed probability that the mutation appears. Fitnesses are independent of n, and there is an inequality, which do not have discrete counterpart. There is an inequality, and the limit process depends on this inequality. What does this inequality say? It's hard to understand. The W bar is the highest fitness in the population, highest possible fitness. And this inequality relates the base measure with fitness. It fails. So it's other side. When alpha has a very low mass around the most fit, or W has a very sharp peak in certain ways, and sometimes this inequality does not hold true. If this inequality holds true, then the limit, so and the theorem says again that the limit theorem, and if we have an additional assumption of compact and purely technical stuff, then the limit process exists, and it's IID process with some sort of measure. And the measure here, it's hard to, it has, if this condition holds, then it has basically W times a probability measure. It's a proportional to W times some sort of probability measure with respect to alpha bar measure. So the density here is with respect to alpha bar measure, and there is some parameters. But if this inequality fails, then there is an atom at the most fit element, atom appears. So there is a lot of constant here. I don't expect you to follow, but let me just say, so the density with respect to base measure is this thing, which is really the continuous counterpart of what we had this discrete case. You might wonder, so this is the discrete case. Well, alpha bar is now the letter C, so you see it's pretty much the same thing. You might wonder, here is no alphas, but it's density with respect to alpha bar. If we want, for example, if alpha bar has a density with respect to Lebesgue measure, and we have to want to have density with respect to Lebesgue measure, we have to multiply this alpha. Is exactly the same thing. So if this equality holds, then it's completely counterpart of the discrete case. But if this inequality fails, bingo, an atom appears. And that's what I did. I didn't expect it. That really doesn't match with interest where this atom appears, but it appears. And the same thing with the second theorem, with where lambda is between 0 and 1. Now we have lambda here, lambda where, and there is another inequality, which is, again, if this inequality holds, then the limit process is the continuous counterpart of the discrete one. But if this inequality fails, then the limit process is something else. So the theorem says that if this is compact and alpha is non-atomic, then the limit process extends. And if this inequality holds, that's exactly the counterpart of the discrete one. That was the discrete measure, and that's the density. It was exactly. But if this inequality fails, then an atom appears. But again, the limit is independent of lambda. And you might wonder where the compactness assumption. I am really, with co-authors are really fighting against this compactness. But this is technical proof. It's based on large deviation principle, and the large deviation principle always assumes compactness. That's why it comes from. And that was that is now the very last slide. I exceed my line, and I thank you very much that you have listened, paid attention, and I finish here. Thank you very much.
Thanks to you. Thanks you. It was a very nice talk. Maybe we can ask if there are questions or comments.
At some point you said that you could see something that you could not see. I don't know. That in the box that you had not seen, or it wasn't the beginning of the talk. Yeah,
exactly. In mutation, when we speak about mutation, yes. Do you refer to Dirichlet process stuff, this breeding, yes? Mm-hmm. So what is the mutation, which I understand the mutation. So its mutation is somebody, previously in discrete case, the mutation is that we take out of a ball and that sort of changes it types something which is also given in this finite set. But in my opinion, in this case, so we have here population, and we have population here, and even the population is very large. There is a certain probability that we observe the new member of the population is of the type we haven't seen in the past. It's not in the population. It's really new. That is my understanding of mutation. So it's a new child is born, and it has something which has never been during the history of mankind. That's the mutation. But the important is that this model says that the Boyer-Urn says once you have observed this mutation, you will see it repeatedly. It comes again, again, again. And that's my understanding what Gregor Mendel saw in his garden. So you see the mutation, you haven't seen it at the first time, you haven't seen, but once you have this guy in the population, it comes again, 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 again. So that's why I think it's very important to study this uncountable case, because it matches my understanding of the mutations. Maybe Chris can add something more meaningful about that. Yeah.
Okay, thank you very much.
Yeah.
Thank you. Are there other questions or comments? Maybe Thierry, I don't know.
Yes. Did you consider diploid populations? You're focused on haploid populations.
Sorry, I didn't understand. Can you?
You are focused on haploid populations. Did you consider diploid populations?
Oh, yeah. Well, I think it's not that. So as I said, there is basically no biology in this. Maybe Chris can answer to the question, but I think you can transfer those results into diploid case, but I'm not very sure about this. Mm-hmm. So for me, it's as I said, for me the genotype is just a color or type. I really I really do not want to be 2n instead of n everywhere, like it's in typical in the evolution theory. But it's a good question. But I think you can. I think it doesn't make much difference. But that's just guess. Maybe Chris can argue about it.
I'm sure. Thanks, Jüri. We looked at diploids, but it's hard to make it precisely exchangeable.
Okay.
It's because then you have to sample two, and you're breeding two at a time, and it was hard to make it exchangeable. But maybe we could try harder. And then I thought, well, if we're making this the simplest possible evolutionary model, there are organisms which are haploid, which are still complex, like moss. So you get some essential, but I agree, it doesn't,
Okay.
but it's hard to get the exchangeability.
Okay, another question is that you mentioned the connection with the polia-urn process.
Yes.
And then you mentioned that mutation could create new types, and this is the Hope model. Are you aware of this? Have you heard of the Hope model?
Oh yes.
Is there any connection with this Hope model? When you mentioned the possibility for mutation to create an entirely new type, this is precisely the purpose of the Hope model.
Yeah, that's a good. I have to. Honest answer, I don't know exactly. I have read about this. It's a good question. I keep it in mind and try to find. The connection. It was pretty difficult to find the connection with the moral model as well. And yes.
Yes, but to some extent, if you have the opportunity for mutation to create a new type or a new species, then you have a countable number of types at the very beginning in the moral model. You see, and this is precisely what the Hope-Urn model is about.
Yeah, that's a good. Yeah, it's a good point. I have to think of it. As I said, I do not consider myself an expert of the evolution thing. It's just a particular model I've been working with. But I think so to me the moral model is that it's all goes to the single individuals level, right? The Bright Marshall, it goes to more to the generation model, but the Bright Fisher is pretty much the same asymptotics. Yes.
Okay. Anyway, I have to look at it.
Yeah.
Thank you.
Thank you, Thierry. Are there any more questions or comments? So it was very, very interesting and a very rich talk. I think we have to learn a lot from you. Maybe I just stop now to record. How do I see?